everyone. So in this lecture, our course is gonna take sort of a different turn because we're gonna start looking into the notion of integer programming problems. We talked about them very briefly in the first lecture when we defined the different types of mathematical programming problems, but today we're gonna go closer into them specifically in terms of formulations. We're not gonna talk about solution methods as yet. That comes in the next lectures. So my idea is to present to you a collection of mixed integer problems that appear quite often in different realms, and that somehow they have this structure that keeps being present in different real world problems. So and I think these are important structures that you should be aware of when talking about mixed integer programming. And then we will end up talking about what makes a good formulation. Somewhat differently from LP, having a good formulation in MIP might mean the difference between being able or not to solve your optimization problem. So it's important that we understand what is a good criteria to compare formulations and use, and which is going to become more obvious when we actually look into the solution method for mixed integer programs. So let's get started. So this first couple of videos are going to be about these different types of problems. So before we do anything, let's once again define the problem we have in hand. So this is kind of how we've been looking into linear programs so far. So, and if you remember, we have this sort of form where we assume that our variables are continuous, and even though we're talking about linear, the main feature about this is not only the fact that it's only formed by linear and affine expressions, but because our variables are assumed to be continuous. And what is going to change now is that whenever we are talking about integer programming, there is a word that is hidden here, that is the word linear. So we'll still assume linearity in our model, but what is going to change is the domain of the variable x, our decision variables. So now we will assume that, for example, if we're talking about integer programming, that our variables, they must take integer values. So they will be defined in the realm of integers. Like, I don't know if you remember our very first example about that carpenter who was making tables and chairs. Now we'll be able to impose a condition that the number of tables and the number of chairs, they have to be integer. Only 3 or 4 chairs, nothing of this 3.3 or 3.4 chairs. We say that we have a binary programming problem, even though, being truly honest, we tend to call binary programs and integer programs as well, but it just means that all our variables, they are defined on the realm of binaries. It typically means that we are, these variables are denoting things like yes or no, true or false, a belonging relationship, whether it belongs or not to a set. So, and we model this using these values 0 or 1. And perhaps the most common of them, at least in a practical sense, is the mixed integer programming problems. So mixed integer programming problems are those where some of your variables behave like we see, so they are real valued variables, and some of the variables are either integer or binary, right? So in this case here, we would have p integer variables, and the remainder of the remaining variables would be continuous, defined as we saw before. And the most important thing, one important thing is that behind these, we are also assume linearity in the constraints, and your objective function and your constraint being affine, right? So one close relative to integer programs is the notion of combinatorial optimization problems. So mixed integer programming or integer programming, it is just like it is in mathematical program is in general a language to represent optimization problems by means of mathematical programming models, mixed integer programming plays this role for combinatorial optimization problems. So it's important that we never lose, to some extent, we don't lose track of the notion of a combinatorial optimization problem, because there is a lot that we can learn and a lot we can exploit by looking at the problem at hand as its original root of a combinatorial optimization problem. You actually see that many textbooks on mixed integer programming and integer programming, they would sometimes they would say integer programming and combinatorial optimization, or vice versa. So what is a combinatorial optimization problem? Basically, a combinatorial optimization problem is a setting in which you're trying to make a selection among a domain of possible selections. So this selection is what I'm calling this subset S. And in a way that you're trying to minimize some sort of cost associated with having the element belonging to the set, and that selection being made in such a way that that selection satisfy a feasibility condition, which here is represented by a subset of our original domain. So basically, among all possible combinations I can make, some of these combinations are feasible, and I'm trying to find that combination that is feasible and minimizes, has associated with it a minimum cost. So the main thing here is this notion of combinations, right? And this family of feasible subsets. So I'm gonna, in the first couple problems, I'm gonna try to, trace parallels with this thing. So just to make sure it's clear that you see that there is an important connection between this and the notion of mixed integer programs. Integer programs more specifically. So for the connection between combinatorial optimization problems and integer programs actually is bridged, if you wish, by the notion of having these variables that represent incidence vectors. And they basically are used to represent the notion whether an element belongs or not, doesn't belong to this subset S. So I can fully characterize one subset S by having this incidence vector, which is basically a collection of positions with 0, 1 values, where whenever it takes value 1, it means that the element belongs to the set, and 0 otherwise. And you can see that this then, has this nature of naturally, if you wish, being a binary variable, because it naturally becomes a variable that can then take this or this value in each component, and you're trying to figure out which is the best value to take. So what bridges it is this really powerful notion of having these incidence vectors for working as your selection variable. So let's see how that works in different contexts. So the first of them, perhaps is the simplest of them, is the notion of an assignment problem. So here I'm posing it in means of workers and jobs, but you can basically assign anything to anything. And the main point, or the main setting of the problem is that you have a collection of workers and a collection of jobs, and you presume that the number of works and the number of jobs are the same. And in this case, and what we're trying to do is to make an association between a worker and a job, right? And I know that whenever I associate a worker to a job, I have a cost Cij, which is represented here. And the idea is that I want to define what is the minimum cost association I can make between workers and jobs, so that I get all the jobs done. So for each job I have one worker, and from one worker I have one job, and the total cost is minimized. So you can see that the combinatorial nature of the problem allows me to represent it as a graph, where I have these nodes and connecting them with arcs, and each arc basically represents a possible connection, and associated with each arc, basically what I'm trying to form is the set S, which is a subset of these arcs, such that the condition one worker, one job, and one job and one worker, this one-to-one association is satisfied. So one possible solution would look like this. And these are the arcs. For this solution, I decided to belong to that subset S. And you can see it is feasible because indeed one worker is connected to only one job and vice versa. Okay, so how do we model this as a integer program? In order to model this as an integer program, we're going to define those variables xij, which will represent whether the work I is assigned to job j, meaning that the pair ij then it belongs to the solution I'm considering. So that said, what I'm going to do is I'm going to look into minimizing the sum in I and j, making this a bit prettier, like so. I in n, j in n of Cij xij. So this is the total cost of the association I'm making. And I have basically two constraints. One constraint that says that whenever I'm looking at a worker I, and I think all the possible jobs that can be assigned to it. And when I sum along these possible jobs, so this is J1, this is Jn. When I sum along those, this has to be exactly 1. So that means that when I look at all jobs, all workers I, and I sum along the job j's, I have to see only one job being assigned, and that can be seen that by doing so. And that means that I have to repeat that for all worker I. So that means that in that example there, for worker 1, I would have something like that. Worker 1 doing job 1, worker 1 doing job 2, plus worker 1 doing job 3, plus worker 1 doing job 4. This has to be 1. So if, say, this variable takes value 1, the others immediately have to be 0, because otherwise it won't satisfy. And I have to have at least one of those being 1 because it's an equality. So that's a powerful mechanism that we use quite often in integer optimization, or integer programming if you wish. And likewise, if you think on the perspective of the job, then you think that the job can be done by several workers, can be done, say, by worker 1, or can be worker 2, 3, all the way to worker n. And likewise, when I add in, look at these, perhaps I should say that each of these are, your xij variables, of course. What you get is that something that looks like this: the summation in I of xij also has to be 1 for all j. So if you think about job 1, this will look like is like this: worker 1 doing job 1, or worker 2 doing job 1, or worker 3 doing job 1, or worker 4 doing job 1. That is also has to be equal to 1, right? And that's all we need. And of course, we have to define that our variable is binary. So if that is clear, so this is how it would look like. The model would look like. This is the formulation for our model, and that summation on all jobs, and the summation on all workers. And here is like I said, I'm gonna keep showing these briefly, but so this is would be the parallel between a combinatorial optimization problem and this formulation. So you should think, what would be our set n? Our set n would be all possible pairs of workers and jobs. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 1, 2, 3, 4, 4, and so on. And the feasible set F, meaning that what are the feasible subsets for this problem are those all that pairs ij appears exactly one pair. So in which I and j appears exactly one pair. So you can't have I1, J1, and J2, and you cannot have so say J1 and then you have I1 and I2. This you cannot have. They have to appear on only exactly one pair. That's the feasibility condition. And the variable, the selection variable, the incidence vector, is basically selecting pairs. So basically when you look again at that picture, I'm looking at all these possible combinations and looking, the feasible ones will be all connections. This would be another feasible solution where each node appears only once in a pair, and a solution is a selection of pairs on the node. So 1, 2, 3, 1, 2, 4, and 4, 3. All right. So this is the assignment problem. Another problem I wanted to look at is the knapsack problem. Sometimes it's said the 0-1 knapsack problem. This 0-1 here is just saying that in this case, you presume that an item can only be selected once. Okay. So what are you talking about? Well, the story goes like this. We have a collection of any items that we have to make a selection from. And there are two things we have to consider when we select an item. That the item has a cost for being selected, of which I have to take into account considering a budget that I can spend. And each value also has, in terms of a trade-off, a value associated to it. So it means that every time I make a selection, I make an item part of my selection, I win CI, but I get discounted AI from this budget B. So the knapsack originally posed thinks about this B being a weight budget. So you're a traveler and you want to fill your knapsack, your rucksack with the most valuable items you can find. But you have to take into account that you are limited in weight. So you want to somehow maximize the trade-off, maximize benefit while, making sure it fits in your knapsack. So here is an example, a graphical example trying to explain the logic of the problem. You have this item 1 that, let's say, is, so this is the weight associated with the items, and this is the value associated with the items. And just for the sake of the example, let's say that they are in order, that C1 is less than C2, less than C3. It doesn't really matter. So basically what you would be trying to do is, if this is the case, you could make item 4 part of your knapsack, and that will take this much of your knapsack. And it seems that with that space here, you can't really do much because this seems to be smaller than that, right? So another option is, instead of then greedily selecting C4, is to select C2 and then select C3, because they are certainly greater than C1, because C2 is greater than C1. And so then it's in these two, they definitely fit on my knapsack, like here. See? So the question would be whether, if C4 is greater than C2 plus C3, then use C4 instead. Otherwise, pick these two, because even though they are not as valuable as C4, the combination might be, and they too satisfy the budget constraint. So that's kind of the notion. That's the dilemma behind the knapsack problem. And how do we and you can see this is a powerful setting that, it doesn't really only relate to knapsacks. A very classical instance of the knapsack problem is the project's portfolio selection. So you have a collection of projects, and each project has a calculated net present value, and they also have all a capital expenditure. And what you're trying to do is to maximize the total net present value from your portfolio while making sure you're not going over a given budget. So that's another example that's actually it's quite more common than actually the knapsacks. So how do we model that? Well, it's simply we use these variables xi, which are going to tell us whether an item was selected or not, and we're going to use, like before, these binary variables, let's say yes and no. And once that is done, what we're trying to do is sum I in n of ci xi, which we are maximizing in this case, and we are considering basically a budget constraint, which is the sum in I of ai xi lesser or equal than b, and xi is binary for all I in n. And that's the model right there. So that's our budget constraint, and that is our value of the knapsack. So in that case, what we'll have is x1, x2, x3, and x4, right, in the previous example. And then the objective function is c1 x1 plus c2 x2 plus c3 x3 plus c4 x4. Let me move this down a bit so you can see. And if I make it, my selection is 0, 1, 1, and 0. My final cost is c2 x2 plus c3 x3, which, by the way, should actually write like this, because x1 is 1, and that's what I was trying to show. So that's how it kind of selects the costs. And likewise, you will have A2 plus A3 less than B, which hopefully is the case, so this is feasible. I think the parallel to the combinatorial optimization problem is rather simple. So basically now your n set is as big as the number of items you have. So it's n factorial because it's all possible. It's not n factorial. It's actually n squared. No, the other way around. Sorry, it's 2 to the n. That's what I'm trying to say. It's a bit early. Sorry. Because it's basically for each item you have two options, right? Whether you select it or not, all the way to item 1, item 2, item 3, item n. So this is 2 times 2 times 2, which is this number of possible selections. And those that are feasible are those that satisfy a cost not greater than b, a cost in the sense of the weight. And your incidence vector is clearly it's literally an incidence vector where each of these components of your variable x takes 0 or 1. All right. So the last problem in this video is what we call the generalized assignment problem. So we just seen the assignment problem before the knapsack. So now we're talking about the generalized assignment problem, and you can think of the generalized assignment problem as a combination of knapsacks and assignments. So basically, you can think of it as having multiple knapsacks to which, so you have the notion of bins, where you can think of each bin as being a knapsack. And what you're trying to do is to make sure your items are allocated to bins or knapsacks. So you're trying to distribute the items to all the bins. And in this case, you can have different number of items and different number than the number of bins. So that's the difference between the assignment problem. And each bin has a capacity bj, can be a cost bj, b, like a cost limit b, like a budget b. And each item has a weight I. So it's just like a knapsack. But now you have this notion of different weight limits. And the difference is that whenever you put an item on a different bin, you get this cost Cij. And then what you're trying to do is find a minimum packing meaning that if these two items say that, these item go there, this item go there, I might have a bin that I don't even use. So I could get a solution that looks like this. In this case, I'm not using this one, right? So all items must be packed, but not necessarily all bins must be in use. And let's see, how do we formulate that? That's it's literally a combination of the assignment problem and the knapsack problem. So what we need is, we will have a different set for bins and items. I think we actually have the other way around, M items. So yeah, so items and bins. And we have this variable xij that looks a lot like the assignment variable, which says that if I assign the item I to the bin j, 1 if it's the case, 0 otherwise. And we're going to use exactly the same constraints we've seen before. So I'll just pull them here and go over them, and they look like this. So so generalized assignment problem is minimizing the total. So here I'm minimizing the cost associated with the associations, you see, because I'm trying to minimize, I'm thinking about a cost, but you might as well could have a value, just like the knapsack. So that means that you actually want to try and maximizing the bin assignment. It doesn't really matter in this case, it can be either way in all them, really. So the main constraints here, this is saying us that all items have to be assigned to one bin. So this relates to that picture we drew before, where I had a node I, and I'm thinking about all bins, possible bins that I can assign it to, and I'm saying that it's being assigned to one of them. And this one here is the knapsack constraint that we just seen. So for each of the bins with its respective capacity B, I am looking at everything, all the items that have been assigned to it, and making sure that the accumulated weight is less or equal than B. So this is a knapsack plus an assignment problem, you see. And likewise, xij is binary. So I hope by now it's a bit clearer how would be the parallel to the combinatorial optimization. But this thing I'm doing of reminding you of what is a combinatorial optimization problem associated is just you reminding you that there is a strong link between combinatorial optimization problems and integer programs. And very often what is known about properties, methods, the body of theory behind, the combinatorial optimization problem version of this can be and often is used to develop solution methods and solution strategies for these problems. I think this is a good stopping point for this video. In the next video, we'll carry on with other examples of mixed integer programs. I think integer and mixed integer programs. So see you in the next video. Bye bye.